Let's discuss results for continuous maps and homeomorphisms. Hello everyone. First, let's discuss the composition of continuous maps. Let x with t, y with t1, and z with t2 be topological spaces. If f, a function from x with t to y with t1, and g, a function from y with t1 to z with t2, are continuous maps, then the composite function g with f from x with t to z with t2 is continuous. Now, let's discuss the restriction of a continuous map. Let x with t and y with t1 be topological spaces, f a function from x with t to y with t1 a continuous map, a subset of x, and t2 the induced topology on A. Further, let g be the function from a to t2 to y with t1 be the restriction of f to A, that is, g of x equals f of x for all x in A. Then g is continuous. Now, let's define open and closed maps. Let x with t1 and y with t2 be topological spaces and f a function from x to y. We say f is open if for all u in t1, f of u is in t2, i.e. the images of open sets are open, and f is closed if for all a closed subset of x, f of a is a closed subset of y, i.e. images of closed sets are closed. Next, let's discuss the inclusion map. Let x with t be a topological space, let a with ta be the subspace of x with t, and let I go from a to x with x maps to x, the inclusion map. Then I is continuous. Further, let's talk about the natural projection. Let x with t be a topological space, let y with t tilde be a topological space, and x cross y with the t prod the product of spaces, i.e. t prod is the product topology on x cross y. Let pi sub x go from x cross y to x given by xy maps to x, and y sub pi from x cross y to y given by xy maps to y be the natural projection. Then pi sub x and pi sub y are continuous and open. Now, let's define continuous maps on a product topology. Let A with t1, x with t, and y with t tilde be topological spaces, t prod the product topology on x cross y. Let f of x map from a to x cross y be given by f of a equals f1 of a with f2 of a, where f1 is a function from a to x and f2 is a function from a to y. Then f is continuous if and only if f1 and f2 are continuous. Let's now move on to defining a homeomorphism. Let x with t1, y with t2 be two topological spaces and f a function from x to y. Then f is called a homeomorphism if f is bijective and both f and the inverse of f are continuous. Two topological spaces x with t1 and y with t2 are homeomorphic if there's a homeomorphism between them. Let's now discuss some remarks about homeomorphisms. Being homeomorphic is an equivalence relation. F from x with t1 to y with t2 is a homeomorphism if and only if it is bijective, continuous, and open. A map f with x to t1 to y with t2 can be continuous and bijective, but not a homeomorphism.
As ever, thank you for watching.